Hey, it's Mr. K doing another video for AP Physics C and 1. We are still talking concepts, and just had my potatoes. If you watched the last video, still working on my coffee. Got some chickpeas going on the Instant Pot. I'm gonna make some falafel, and don't forget about these guys that you can collect throughout the year. Turn them in at the end of the year or whenever you want, or have them as keepsakes. I'll print more out from year to year if I keep on doing this, but they will be worth things as we go on throughout the semester and the year. Right now, fish coins are worth late grades being taken off of assignments because for some reason people keep on turning things in late. Well, moving on, I'm gonna give you a kind of a run through practice on just looking at forces. Now here we have what's called an inclined plane. This inclined plane is inclined at some angle theta above the horizontal. There's another video that I have that's going to be more mathy, that's talking about how to solve for all the numbers of the inclined plane. Right now I just want to talk about how to do a free body diagram for it. So at the moment, let's say that there is no friction on the inclined plane. Let's say that gravity does exist and the object starts at rest. So we have just placed this block on the inclined plane, and what's going to happen? So what you should say is, well, Mr. K, the block has just been placed on there, and it's just going to slide down, accelerate that way. It's not going to slide down at a constant rate because there is no friction. So it's going to move that way. It's going to speed up. So that should work out. So let's draw the free body diagram. So we know, I'm going to use blue here for this one, that there is a force of gravity on this object that points downwards. Again, we're going to call that mg. Okay, now if that was the only force, this thing just falls straight down, which does not happen here. So something has to be pushing it to the right if it's also moving down and to the right. So that's going to be our normal force. Remember what that is? Normal force is going to be the force of reaction of pushing into a surface. So that surface is going to push back on you. So here's my surface. Normal force would be normal to the surface, which means perpendicular to. So I'm going to do a perpendicular to my surface there, and it's going to go up in this direction. Now I'm going to be careful on the length, because normal force, do Fn for that, normal force should not be any longer than force gravity in this case. That would be kind of weird if it was, because gravity is the reason why normal force exists here. And so if I was to look at this free body diagram, that's it. Again, frictionless, thing was just placed on there. That's all we got. Now, we know that if this object was to slide, it would slide along this axis, the axis of the inclined plane, up and down the ramp. And so just to show you real quick, here is that same axis. And if you notice, let's do one that's perpendicular to that, that's along that normal line. Do you see how gravity has a piece of it going in that direction, and gravity has a piece of it going into the inclined plane? Let me use red to show you what I'm talking about. So gravity is pushing into the inclined plane like so, and that's why normal force exists. You know, gravity is pushing this block into it. And then gravity also, the force of gravity is also pushing it this way in the direction of our incline. So if we were to tilt our heads, that would be true. Now, if we didn't tilt our heads, then normal force was doing that action to the right. So it kind of depends on how you're looking at it. If you're looking at it like normal, then normal force is the one doing it. But if we tilt our problem, which we will in the future tilt our problem, it's going to be easier to actually look at it that way. What I mean is like this, because then we're just moving left and right. But for now, let's just keep it as is. All right, let's run another one. So what if this object was moving for a while? We had placed it on here and it's sliding down the inclined plane, still no friction. What would the free body diagram look like for that? And the answer would be the same. It's still got force of gravity on it. It's still got normal force going that way. There's no friction, so there's no reason to draw it. Okay, but now it's moving. Now it's accelerating. It was accelerating before, but now it's moving with it, velocity-wise, and accelerating. Let's see. What's another one? What if we had friction? What if we had friction? What if this block was just at rest? It was stuck. Okay, if it was stuck, Let's draw another free body diagram here. Again, so the trick to drawing these is asking yourself what forces are involved in this problem. The main force right now is force gravity. So just, there you go. mg. Boom. Now, is it on a surface? Well, surfaces push back perpendicular to themselves. That's going to be not this way, but angled a bit. So I hope I did that right with my camera. We'll see. So it's going to be this way. So normal force will point off at an angle to us, and again, perpendicular to your incline. The surface is here. But it's stuck, right? So if it's stuck, that means it's not sliding down into the right. So it's got to have some kind of force the other way. And that's going to require a force this way. And we're going to say that this force is the force of friction. Friction is going to act parallel to your surface. Okay, if you do this, friction right now is acting up and down and up and down and up and down and up and down, trying to oppose the motion of my hands, depending upon which one I'm talking about. Okay, but that goes parallel. Now my hands are going to push in towards each other, and they're pushing in like this. It's normal to the surfaces. Friction, we're going to talk about that much more in detail. There are two types. One is kinetic friction, turns energy into heat, and the other one is static friction. It's kind of just stuck. It's stuck. But that scales up until you can break it and then things start to slide. So this is a free body diagram in the case of, hey, this thing is just stuck on the ramp. Okay. What if this thing was sliding down the ramp with friction? Okay, thought, think about it. It would be this one. Sliding down the ramp was this, but then we add in friction, and it's this. Now, we could say it's sliding down the ramp at a constant velocity. It's still this. We can say that it's sliding down the ramp and it's accelerating, which would mean that friction's probably a tad bit smaller. We can say that it's sliding down the ramp and slowing down, which means friction would be a tad bit bigger because it would be slowing the object down. Our net force would be in that direction, not that way. Let's draw another one. What if this thing was sliding up the ramp? Okay, with friction. Sliding up the ramp with friction. So if you're not sure, then let's draw our forces. We've got our force of gravity, still going down. We've got our normal force, still normal as it was before. Okay, may have drawn that one a little bit long, but whatever. But now it's sliding up the ramp, so friction, it's opposing the motion in this case, slowing us down. Friction doesn't always oppose your motion, by the way. People always say it does, but it doesn't. Like think about how you walk, right? You're kind of using friction to push the ground backwards, but the ground's friction is pushing you forwards. You know, put something in the back of a truck. How does that thing accelerate forwards? It's friction. So let's see. This thing is sliding up the inclined plane. If it's sliding up the inclined plane, friction's probably going to face opposite. This is that special kind of friction called kinetic friction, sliding friction. The other one was called static friction. And that's it, right there. So we can see that we have two things pushing in that direction. One is going to be friction, the other one's going to be the force of gravity. Because remember, the force of gravity was trying to slow us down in the first place if we're moving up the inclined plane, or it's speeding us up if we are moving down the inclined plane. But yeah, I'm trying to keep this as a conversation like we would have in class, just in case you missed it. So just keep on thinking about things. So we have this thing sliding up the ramp and slowing down, most likely. That's this case. Sliding up the ramp and speeding up, that kind of doesn't make too much sense unless we have something pushing it from behind. I'm going to stay away from that for right now. Let's do one more. What could we do? Let's put something. Oh, let's just do this. Let's make it not a box, but let's just make it like a ball. Here, let's do that. Use my little compass, and let's do this guy. Okay, so I'm going to put this ball on the ramp, and then the question is, what would the free body diagram look like for the ball that's on the ramp? Okay, and this is far in the future where we really look at the dynamics of the ball, but we can still do free body diagrams for it. So you put the ball on the ramp, and here we go. There's a free body diagram, and we have our force of gravity, which goes straight down. It's still called mg on the ramp. The ball's sitting on the ramp, so there's still normal force there. So the normal force would go in that direction. So that still definitely exists. But then, is there friction or is there not? Let's say there is friction. You know, we've had the friction here for a while now. So let's say there is friction. Which way would friction point, and what would it do? And so the answer to that would be, it would point up the ramp. Okay, it would point this way. So friction would point that way. We place the ball on the ramp. Friction points up the ramp. And you know, this ball doesn't like slide down, it rolls down. So the reason for the rolling of the ball is because of friction, causing what's called a torque to make it spin, and that's gonna be a future topic. But that friction is still there. So if we were to say, hey, we've got a friction ball with friction, and we've got a block, which one slides down the ramp faster if there's no friction? They should go down at the same rate. But if there was friction, it turns out that like the block would actually make it down to the bottom first if there was like similar types of friction involved, because a lot of that energy is being converted to the spinning of the ball. Anyway, too much. So we'll stop it here. Just looking at free body diagrams, and just interesting things to think about. You know, this is more of a conceptual video.